Hello, Easy Projects here, and welcome to Chip Chat. So I thought it could be fun to do a few episodes where I pick some random popular chips and make some circuits with them and see what we can use them for. And today we will take a look at the CMOS 4069 inverter chip. And the CMOS 4069 chip is very simple. It's just 6 individual inverters, and it's powered from a positive and a ground pin. And it can in theory only do one thing, that if we put a 1 here, a high voltage, we will get a low here. In the other case, if we put a low here, we will get a high here. And if we tie these two together, if we get a high here, we will get a high here, and if we have a low here, we will have a low here. So that's all great, but inverting signals is not that fun, so we will need to find something else we can use this for. So we can build a latch out of this chip by using 2 of the inverters, and we'll tie those together. And these are powered from the VDD and the VSS. And if we tie the other input and output together with a resistor, we have our latch. And we will put a small light bulb at the output here. And we will add 2 momentary push buttons. One that goes to VDD and one that goes to ground. So now what happens if we press the ground switch? We will set a 0 here, and it will not short out this inverter here because we have this resistor. But it will set a 0 here, we get a 1 in the middle and a 0 here again, and this resistor will also keep this input at 0, so it will stay at 0 and the light will be off. And now if we briefly press the VDD, we will set a 1 here, 0 in the middle and 1 here, and this resistor will also keep this a 1. So when we release the switch, the light bulb will still be on. So now we can try to build this on the breadboard and see if it actually works. And here we have it. So we have the 4069 chip in here. We have the resistor, and we have a current limiting resistor for the LED we will use as a sign to see if it's on or off. And I have my 2 switches. One is connected to ground and the other is connected to plus 9 volts. And you can see right now the LED is off. So if I press the off button, nothing will happen. But if I press the on button, it will turn on. And nothing happens if I press it again. And if I press the off button, it will turn off. So that's simply everything it does, but it can be useful for some things. And of course we could make this to be an inverse of what we started with by moving this one to another inverter. And connecting the input of this inverter to the output we were using before, like that. So now when we press the on button, it will turn off. When we press the off button, it will turn on. Very simple. And we could of course change this LED to a red one. Put another resistor in. And put a green LED across the non-inverted output. So now if we press the off button, it's of course red, and when we press the on button it will change to green. So I don't know if that could be used for anything, but... And that last circuit was this one over here, and just forget about that. So now that we started to use 3 of the inverters, we can make another circuit that will not be as stable as this one. So let's take a look at that one. So if we once again take 3 of the inverters and we just put a jumper across there so they are all connected in one chain, then we will try to set a 1 here, and that will be a 0 here and a 1 here and a 0 here, but that's already a 1, so what will happen? Well, you might think that the chip will short out and blow up, but that's actually not what happens, because there's some delay for this one to get through to the other side to be a 0. So there's a delay for this, a delay through here, and a delay through here. So when this one becomes a 0, and before it gets all the way to the end again and becomes a 1 again, there will be some delay. So this will be an oscillator. And you can make an oscillator out of every odd number of inverters. So you could have 3, 5, 7, 9, or whatever you want. But the more inverters you have, the longer the delay will be, and therefore the slower the output frequency. And you can find all these delays in the datasheet, but in my opinion it's easier just to try it out and see what works. So let's do that. So here's the circuit, and it's even simpler than the other one. We just have 3 jumper links, one going from the output of the first inverter to the input of the next, and from the output of that one to the input of the next, and then this one goes from the output of the last inverter to the input of the first inverter. And again it's powered from ground and 9 volts. But to see if this works, I guess we'll have to turn on the scope. And here we have it on the scope. As you can see, it is oscillating. We're not getting a square wave on the scope because the chip is running as fast as it can. Because as soon as one inverter sends the signal to the next, and that one sends the signal to the next one, then it switches low again. So, and you can see that the signal is jumping a little back and forth here also, so it's not too stable. And this is running at 12.66 megahertz, and there's really nothing we can do about that with this setup, but we can add a few components so we can adjust the frequency. So we'll try to make a schematic for that and try that one out as well. So now that we are talking about delays, one easy opportunity to change the frequency would be to change one of the delays here, so we can try to do that. We can add 2 resistors. Here, and then connect this again. So now we basically have what we had up here, but we added 2 resistors. Then we'll add a capacitor from here and down to here. So when this one have to change the state of the next one, then it will have to charge or discharge this capacitor first. So depending on the value of these 2 resistors and that capacitor, the frequency will be changed. And we can only lower the frequency. The 12.66 megahertz is the absolute maximum we can get out of this. So if we add anything in here, we will lower the frequency. And when we're talking about adjusting the frequency, we can put a a variable resistor between the inverters and the capacitor. So by changing the value of this resistor we can change the frequency even further, but only in a limited range, because if this value gets too high then it will become unstable. So let's try to build up these two and test them as well. So here we have that circuit, and I've just placed two 1K resistors instead of the jumper wire that was across the last output and the first input before. And I have added a 1 microfarad capacitor, the grey one there, and I have added a trim pot here, but that's turned all the way down right now, so it's effectively not there. And we will probe the output. And as you can see with these values, the frequency is 1.58 kilohertz. And I can try to adjust the trim pot. So now I'm making the resistance from the capacitor to the inverters larger, and the frequency should rise, and it does. And we're now up to 4.5 kilohertz, but at some time you'll see the signal start to get very unstable, and very soon it'll just disappear like that. So it's only for trimming. It can't really go all the way up. But I mean, you can adjust it a few hundred hertz. If you're aiming for 2 kilohertz, you can easily set that by doing it this way. Just like that. And just once again noticed how unstable this is at higher frequencies. It's jumping almost a whole division back and forth here. And since this is in the audio range, we should be able to get some audio out of this piezo speaker here. So let's try to put this one in. And I don't know if you can hear that, but it's screaming. So now let's try to adjust the frequency again. Now we can easily hear that it's going up in frequency. Whoops, now we can't hear it anymore, and it's starting to disappear. But just notice how stable the signal is. And if I turn this slowly down again, you might be able to hear that it will change frequency in clicks. Click, 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 click. And we might, if we turn it very slowly, we might be able to catch a point where it's just about to change. Like right there. You can see it's very unstable in the frequency. So what happened here is we built ourselves a crystal oscillator. So we're actually using the piezo speaker as a crystal, and it's acting as a feedback for the inverter oscillator. But this is not the most optimized circuit for doing that. But as you saw before, the signal was flickering back and forth when we didn't have it in, and now when we have it in, we can find these spots where it's almost not flickering. But again, if we turn it up, it just disappears. So let's turn this down again. Like that. So let's try to optimize this circuit a little bit, but still using the piezo as a crystal oscillator. So what we just did was to put that piezo speaker in here, and this will act as a resonator and it will stabilize the circuit to a specific frequency, and that will depend on the resonance frequency of this piezo speaker. And if we didn't want this to actually interfere with this, if we just wanted to use it as a speaker, we could delete this and we could put this into another inverter, and we could put it on here. In this configuration it would not interfere with the oscillator, and we could choose any frequency we wanted to play on the speaker. So I've just drawn exactly the same schematic once again. But what we can do, instead of put the crystal over here, we can put it across the first inverter, like this. Or we could put it across the second one as well, I guess, but this is what I did. And by putting the piezo across one inverter instead, we'll get it stable at much higher frequencies, so we can go up to maybe 100 kilohertz. So now let's try to take a look at this one. So I'll try to turn up the frequency. Now we can start to hear the speaker. And it will still lock to certain frequencies and be unstable at other frequencies, but we should be able to get much higher frequencies with this. So we're already up to 31 kilohertz. Oops, that's unstable. And that gets stable again, we're up to 80 kilohertz. And now we're over 100. Yeah, so we're up to 125 kilohertz, and this is the maximum for this setup, but you could probably change some values and get it to resonate at different frequencies. But the only problem with this is if I touch this, it will go very crazy, because I will change the resonant frequency of the disc. But as it's just standing there in free air, it's actually very stable at a lot of frequencies. But yeah, it's just an experiment, so you can try to play around with it if you want. If you find anything interesting, please let me know. So this leads me to the final and maybe the most simple circuit that I will show you, because we will only need one of the inverters. And we'll need a resistor, like that. And that have to be a high value. We could say, I don't know, 4.7 mega. Oops, I need to draw there. And we'll need a proper crystal oscillator this time. And we could choose any value we want here. So we could make this, let's say, 2 megahertz. And we will need 2 capacitors. And they both will go to ground. Like that. And these have to be very small as well. Maybe, I don't know, let's say 15 picofarads. You can actually find these values. These are load capacitors for the crystal, and you can find that in the data sheet for the crystal. But I don't know. If they're not too high, it will work. But if they're too high, the crystal will stop oscillating. So that's an easy way to find out. But of course, if you're designing something, you should use the proper values. And if you work with microcontrollers or anything like that, this will be a typical configuration for that, because then this will be, there will be some oscillating circuit inside the microcontroller, and you'll have to add a crystal and 2 capacitors. So that could be something like this. I don't know the exact internals of the microcontroller, but this configuration is very used for setting the clock frequency of a microcontroller. And this will of course be a fixed frequency, and you'll have to change the crystal to change the oscillating frequency. So we can try to build this one up. Well, so I ended up using 22 picofarad capacitors instead, because I didn't have any 15. And I used a 4 megahertz crystal instead of a 2 megahertz, because I didn't have any 2 megahertz. But anyway, I think this will work. So let's take a look at the scope. Ta-da! And we got 3.9999999 megahertz. And again, it's not a square wave, because the chip is not fast enough to do 4 megahertz. So if we took something lower than that, it probably would look like a square wave, but yeah. So I think that was basically all I could think of uses for that chip, but if you have any, please post them down there. And if you like these chip chat videos, please thumbs up and subscribe to my channel. So see ya next time.